Welcome to a lesson with Dr. Powell. Let's look at another application of a definite integral. Remember the example that we have of a volume and the derivative of volume with respect to a parameter h as, as is depicted here, and how it was simply the cross-sectional area. At this particular value of h, we're thinking about increasing volume as h goes this way. So the cross-sectional area is just pi times the radius here squared. The radius is just 1/3 of the height, as we can see from the bigger shaped cone. So we have pi times quantity h over 3 squared, and that's the derivative of the volume with respect to h. Now, using this rate of change, we can compute the volume of this little piece right here of the cone from height 1 to height 2. We can actually just find this rather quickly, even without having the formula for volume. What we can do, in fact, all we're doing is finding we just find, it doesn't matter which antiderivative we find even. Here, we're not looking for a plus c or anything. So what we can do is we take the definite integral, which computes the change of the volume function, which is what we wanted. We'd find the change because we know its derivative this is its derivative. So we can compute the change of the antiderivative simply with an integral. Now notice that we have pi, and then we have, if we distribute this square, h squared over 9, the pi over 9 is like a constant multiplied on, which, just as for derivatives, works for antiderivatives. You can factor it out. So it's factored out, so it's pi ninths times the integral from 1 to 2 of h squared dh, which ends up being pi ninths times h cubed over 3 from 1 to 2. So we can plug in 2, plug in 1, factor out the constant, which is pi over 27. Plugging in 2, you have 8. Plugging in 1, you have 1. So 2 minus 1 is 7. We end up getting 7 pi over 27 as the area of this piece. And we did so just by using a definite integral and using this particular derivative. Thanks for watching.